I have the pleasure to introduce Inga Kamp, the first speaker of the group series. She is at the University of Groningen in Netherlands. She did her PhD at the University of Kiel in Germany. After the PhD, she got a Marie Curie fellowship. She moved to Leiden in Netherlands, and she stayed there for 4 years working with the Evidence group, which is a very well-known astronomical researcher. And after that, she got a contract with the ICE, and she moved to Baltimore to work with the HST. And after the HST, and she worked there for 4 years, she moved back to the Netherlands, and she's now at the University of Groningen. She's going to talk about the new window into planet formation with James Dwarfs. Thank you very much for coming here at the lecture.
Thank you very much for the invitation. I mean, it's a pleasure. It's my first time here in Barcelona, and I'm really enjoying my day. So thank you very much for bringing me here. I would like to tell you a little bit about the amazing journey we took since the launch of JWST, because I'm associated with the project already since almost 2008 when I came to the Netherlands. But I never anticipated that the data would be so rich as it is. And so it has been a super exciting journey of research in the past years. And I would like to share that with you a little bit. So what I would like to touch on today is to just give you a bit of background, because not everybody knows what I'm talking about when I talk about disks and planet formation. So I will give a little bit of a general introduction and then basically present you my very biased view, because I'm part of a guaranteed time observing program, the MINDS program, my very biased view of what we learned from James Webb, just staying with the observations. But then because my second leg is actually modeling as well, I want to push a little bit deeper to say what we can learn from doing very detailed thermo-chemical modeling, how we can actually learn more from these James Webb spectra than just looking at the plain observations. And I will then end with some next steps and conclusions. So our current views of planet formation. I think our views have shifted a lot, and that was mainly thanks to ALMA, because ALMA gave us these stunning, very high spatial resolution images of disks around young stars. So every young star is surrounded by such a disk of material, contains gas and dust, and ALMA has been absolutely stunning in spatially resolving the dust emission, mostly the gas as well, but the dust is the prime, very high spatial resolution observation we have. And we have taken this image. This is the HL Tau system, a very young system, less than 1 million years old. And that was one of the very first images taken with a large baseline. And that disk was not a smooth disk, as everybody thought earlier, but it was falling apart into rings and empty regions. Now, this is very exaggerated in the contrast. Where it's dark, it's not really a gap, but it's just a bit less material. So there are fluctuations in the disk, and we think they are related to the first steps of planet formation. And so that was amazing to see, and it triggered a whole lot of follow-up research, including large programs also that targeted many, many more disks, looking for the substructure that is related to planet formation, but also trying to characterize it, because not all of the disks show these kind of ring structures, but some of them are maybe more still like blobs. We also know now that some actually have spiral arms, and so there's a huge diversity. But in any case, what we see is that planet formation is probably starting very early. And there was even a more recent paper by Segura Cox, where they even saw substructure in a disk that was less than 500,000 years old. So whatever it is that is forming planets, it must start to act very early. I'm not saying this is already full-grown planets. No, these will be protoplanets in the disk, but something is already happening. And of course, by now we have evidence, at least for 2 objects, I think by now even more. So there's a PDS-70 system, which is a very young solar analog star, which is surrounded by a small disk. So I use the pointer. So there's a tiny small disk in here, and then there's an outer disk that ALMA sees. But in this cavity between the two, there are at least 2 planets, maybe even 3 planets. They have several Jupiter masses, so they're very massive, but they are also in resonance, like we know from Jupiter and Saturn in the solar system. So it's a little bit larger scaled version of our own solar system, which is amazing because it's the first time we can actually see disks and protoplanets together in context. And this is another example. This is a disk around a more massive star. HD 169142 is a star which is about 2 solar masses, and also there possibly a protoplanet has been detected. And so I think we now understand that the first steps of planet formation happen very early on, probably within 500,000 years. And I think a lot of people working on the solar system would entirely subscribe to that, because also from solar system evidence, we know that the first steps of planet formation occurred early. Now, the main question is now, of course, I'm researching mostly disks. Some of you in the audience may research exoplanets. But the big question in the room is, how do we link what is happening in the disks to the kind of exoplanets that we get out in the end? Both in terms of, how the system eventually looks like, how many planets does it have? Are the rocky planets always interior to the giant planets? Do we see a huge diversity? But also in terms of composition. Do all these exoplanets have a composition? If they are a gas giant exoplanet, does it have the same composition as Jupiter? If it's a rocky planet, does it have the same composition as Earth? And this doesn't have to be. These disks are very dynamic structures. There's a lot of chemistry happening, a lot of evolution in terms of transport of material as well. And because these disks have a gradient in temperature, so as you go from the central star, as you go away further and further out, because the temperature of the material changes, the material is heated by the star, obviously, you can actually form ices on the surfaces of small dust grains. The disks contain dust and gas, but the moment the gas becomes too cold or the dust grains become too cold, molecules like water, CO2, ammonia, CO, they can freeze out subsequently. So we see a number of ice lines. The first one being the water ice line at a temperature of roughly 150 K. But then those volatile gases freeze out. They become part of the solid in the form of ices. And of course, the planets, or at least the planetary cores, are thought to be made out of solids, but that solids would encompass also the ices. And because of that ice formation, the carbon to oxygen ratio in the gas, which is left behind after ice formation, but also in the solid, which is forming from the ices, changes as a function of distance. Now you can imagine if you build first a planetary core and then you accrete all the gas on top, like we typically think a Jupiter would form, it matters where we are forming the planet for what kind of carbon to oxygen ratio in bulk our planet may have in the end. And so people are trying to play this game of linking what we observe in the stage of the disk, how the material is distributed, how the carbon to oxygen changes as a function of radius, with what we see in exoplanets. And this is just one example from a very early paper about exoplanet atmospheres, including some of the data of the mid-infrared instruments. So you see we go here all the way to 12 micron. And in these exoplanets now we see all the chemical composition of the atmosphere. And there's a huge diversity in these atmospheres as well, containing water, CO2, we have seen for the first time also SO2 actually, a bit less evident here. We've seen silicate clouds. And so the idea is that somehow, now that we can study these exoplanet systems and we can study these disks, that we should be able to actually learn how we get this from the disk. And of course, that is a very nice thought. The problem is in the details in between, because how we get from here to there is a very intricate problem. Because planet formation is not as simple as just proceeding locally. If it was just proceeding locally, we would be in a better stage to make that link. But the paradigm shift that happened is that it's not just planetesimals forming the cores of planets and then you accrete gas on top, but actually pebble fluxes, so pebble accretion, probably also plays a role in planet formation at different distances to different efficiencies. But the way how you have to see this, so pebbles are small dust grains. maybe millimeter size, maybe centimeter size, depending on the surrounding disk. And those pebbles can actually move quite nicely in the disk. They move with very high radial velocities, much faster than any of the big solid bodies. And so the moment we form planetesimals, they are exposed to an ever coming flux of these icy pebbles, small grains, and they can be actually very efficiently accreted because the gravitational focusing helps in the case of pebble accretion, while if you have planetesimal accretion, you really need a hit-on collision. And so the pebble accretion can be a very efficient way of growing your planet once you have a planetesimal to start with, or a protoplanetary core. And so in the end, probably the whole picture of how planet formation happens is a very mixed bag. So you need to form some planetesimals, maybe that is mostly local, but then comes a pebble accretion component, which can be also very non-local. And then comes a late stage as well, where a lot of n-body dynamics plays a role, because once you have a Jupiter, for example, you will shuffle around even planetesimals in the system, simply through gravitational perturbations. And then there could also be a phase of planetesimal accretion. And so all of this is mixed together. But what it tells us is that that whole planet formation picture, planets will form with a lot of non-local material. On top of that, once you're forming planets and the disk is still around, and I showed you the example of PDS 70 and the more high mass star analog, you have those protoplanets in a phase where there's still disk around. If you have a planet and the disk is still there, the disk and the planet exchange angular momentum. And so even the forming planet will move through the disk and then accrete material from different parts of the disk. And that makes this whole story, how to link the disk composition to the planet composition, a very intricate puzzle. But nonetheless, it's a puzzle that we like to solve. And so to give you a little bit of context, this is a figure I took from a review by Till Birnstiel. And what it shows is what happens if what happens in a disk is that I grow my particles in size because of mutual collision. They become larger and larger, with this being like, this being a micron, and this being 1 centimeter. And this can happen at different places in the disk. So at 1 AU, at 10 AU, or 100 AU distance from the sun. And the arrows give you an indication for how fast that process goes. How fast am I growing actually in size, my dust grain, if I start at different locations in size? And how fast does the radial migration work inwards if I am a dust particle of a certain size? So for micron-sized particles, you see there's almost no horizontal vector here, meaning that those particles simply stay where they are, they orbit with the gas. But the moment you make your dust particles larger, so what I call pebbles, they decouple from the gas. And if we look at centimeter-sized particles, they can actually move very fast in the disk. So millimeter and centimeter-sized dust grains, those are these, they can move on timescales of 1,000 or 10,000 years through the whole inner disk. And that makes it a very fast phenomenon compared to the growth of a planet, meaning that a planet can incorporate material from very, very far out in the disk easily. And a second thing to see is also the growth of these grains happens very quickly in the inner disk. Now, the vertical vector is the growth, and the growth also happens on very short time scales. And so very likely we have a lot of these pebbles in these disks that move very quickly through the whole disk. And because if you have pebbles here in the outer part, they contain a lot of volatiles. If they move inwards now and they pass a certain temperature line, those volatiles will sublimate. And so what you do is you actually transport element budget from the outer disk to the inner disk. And if you do it, you will change the carbon to oxygen content of your material. And so that is a very important thing, and that is something that I will come back to later, whether or not we actually see that reflected in the spectra of the inner disk. The only caveat here, so these are calculations that have been done, just using the basic physics. But as I showed you initially, these disks have a lot of radial substructure. The moment you have radial substructure, that kind of migration is hindered. because you create pressure bumps, and pressure bumps in the gas can actually trap dust grains. And so the efficiency of that radial transport mechanism may be overestimated in this simple picture. But again, it's something we need to figure out. And so the cool thing about the James Webb Space Telescope, if you think about this, is that it actually looks at exactly this time and this region of the disk. So we look at disks of the order of, say, 1 million to a few million years, and it looks at the inner regions where we think mostly terrestrial planets are forming. And for that, it will be able to characterize the content in these disks very well. So now let's see what we can actually do with James Webb. Well, this is a Spitzer spectrum that I took. It's an average spectrum for a number of disks. And, you see a little bit here of a signal. The gray is the noise. This is HCN hidden underneath. But actually, when we look with James Webb, this is what we see. And so we see an enormous increase in spectral resolution, which really helps us to deblend things. But we also see an increase in sensitivity. So this is now the C2H2 being very clearly visible. This is still HCN, but with all its raw vibrational substructure. And I can overplot on this theoretical predictions for where these molecules emit. The yellow is a little bit hard to see here, but this is all C2H2 with its raw vibrational substructure and the isotopologue of 13CH2. And these peaks are all from the raw vibrational emission of HCN. So the interesting thing is James Webb will not give us spatial resolution, even though it's more than a 6-meter telescope. It does not resolve those scales, but it provides us the spectral resolution to disentangle the various molecular emission. And so in a sense, these mid-infrared spectra now encode the physical and chemical information of the inner disk in some intricate way. And this is exactly where the rocky planets are forming. And so we want to understand what is the material from which these planets are forming. And what is the advantage is also the disadvantage, because the mid-infrared emission is the product of many processes, unfortunately. So we need to understand the physics, the chemistry, the dynamics, the radiative transfer, in order to interpret what these spectra mean for the composition of the material. So that is our challenge for the coming half hour or so. So I'm part, as I said, of the MINDS program. It's a guaranteed time observing program with about 120 hours. And we targeted a large number of disks around solar type stars, some disks around more massive stars, some older disks, debris disks, but also 10 disks around stars that are much less massive than the sun, about a tenth of the mass of the sun. And our most important focus is to get MIRI mid-infrared spectra. And even though it's an integral field unit spectrograph, we only take the central spaxel for now. We are starting to look at the extended emission as well, but most of what I tell now will be pertaining to the central spaxel, to the inner one, to a few astronomical units. So let's have a look. There are way too many observations and papers we did. I have no time to go into detail. A lot of exciting results coming out of analyzing each and every spectrum by itself. And this is the amazing science you can get out of these disks. Each disk is very different. Each disk really warrants to look at it in a lot of detail, which we did in the first round of papers. And we always learn something new. Now, what I would like to get across is the message that no disks are alike. So they are all very different. And I tried to show that in this overview. So you see here a few of the solar type star disks, and then this is a very low mass star disk. But even if you look at the spectra around these solar type stars, and these are just 3 of our entire sample, and this is the wavelength range where we have C2H2 and HCN, what I also showed you earlier, they are all different. Now, if you look at the relative strength of acetylene versus HCN, they are very different. And then we look at the disk around a very low mass star, again, it's very different. This is a longer wavelength region where we also cover the CO2 emission here at 15 micron, and then a lot of water emission, which are the blue lines here. So the bottom panel is model spectra just to guide our eye, and these are the observation. And again, we see that they are very different. Some objects are very bright in CO2, and they show hardly any water, and others are just full of water lines. And so there's a lot of diversity that we need to understand somehow. And I want to show you this movie, which is a disk around one of these very low mass stars. It's a paper led by my PhD student, former PhD student. So we saw methane emission, ethane emission here. We're just browsing through the spectrum. This is C2H6. This is acetylene, but we also see the isotopologue of acetylene, which is a peak here on the shoulder, indicating very high column densities of material. So it's full of these hydrocarbons. Benzene is the largest one we have seen. But interestingly, there is CO2 and even the isotopologue of CO2 in this disk. We do not see any water, but we see cyanoacetylene, something we expect to form from acetylene. We see diacetylene, propene. So it's one of the richest spectra we have. And it's amazing the moment we analyze this spectra, because we can compare it with the theoretically predicted spectra. What we see is that the column densities of these molecules are so high that they form a quasi-continuum. If we see these kind of bumps in the spectra, they are not because there's dust emission making the spectrum bumpy. This is so much hydrocarbon emission that it forms a quasi-continuum. And that is very interesting to also think about, how to explain that. Now, one of the stunning things that came out building on Spitzer. So Spitzer already told us there was something going on with HCN and acetylene and water between the disks around solar type stars and very low mass stars. But with JWST, we have such a cleaner view on this. And for the first time, we can see hydrocarbons beyond acetylene. Now, the acetylene is that clear peak here, which has been seen previously by Spitzer, but now we see all these brown ones as well. And these are all hydrocarbons. So it tells us that the disks around these very low mass stars are simply carbon rich. There's no other way we can get all these hydrocarbons than demanding that the carbon to oxygen ratio is larger than 1. The moment we do that, we find all these rich hydrocarbons. And this is the solar type disk, and they are all oxygen rich. They show very little hydrocarbons, a little bit of C2H2 and HCN, obviously, but otherwise it's CO2, water, OH, oxygen-bearing species. So there's a clear dichotomy in disks on solar type stars and very low mass stars. And that is, again, something super exciting to understand why that is. And my PhD student also led a paper where he looked at the entire sample. And what we did is we actually measured the dust opacity in these disks by using the peak of the 9.8 micron silicate feature as a measure of how much dust there is, so how much opacity. And then we use the ratio between the isotopologue of acetylene and acetylene itself, so the two peaks in the raw vibrational emission, as a measure for the gas column density. Because 13C-CH2 is a rarer isotopologue. The higher the column density, the brighter that becomes, even though the C2H2 itself is saturated. It's optically thick. But the ratio tells you, how much optical depth, so how much gas column you have. And so if you look at that, you see a very interesting anti-correlation here. So the more dust we have, the less column in terms of gas we see. And the least dust-containing disks show the highest possible column densities of gas. And the way how we try to explain this is by saying, well, these molecules in the disk, they are not just living everywhere, but they live in a kind of layered structure. So probably the first molecule, as you come from the top into such a disk, the easiest to form is water. And then the next one you form is CO2, and below that is C2H2. At least in many of the chemical models, you see that kind of layered structure. And then you can imagine, depending on how much dust opacity you have, you can look deeper or less deep into that disk, which is shown here. So your dust continuum could be sitting above the C2H2 emitting region, or it could sit very well below it. And so depending on where your dust is sitting, you expose larger and larger columns of C2H2. C2H2 also has a reservoir here in the inner disk, where the conditions are very hot, very high density. And so if we have a very, very low dust continuum, we actually can probe very close to the midplane, and we see very, very high column densities. And so that could be part of what we are seeing and why the spectra are so diverse. Now, just to summarize the takeaway so far before I move into the modeling part, I think I showed you that there's a huge diversity in these mid-infrared spectra, so that there are no two disks that are really looking alike. And also, we detected many of these large hydrocarbons, large being relative. I know chemists would not call them large, but to me, anything with more than 2 carbon atoms is a large hydrocarbon. So we see many of them, and we see very large column densities. And then the disks around T-Tauri stars are oxygen-rich. The disks around the very low-mass stars seem to be carbon-rich. And interestingly enough, disks around very low-mass stars still have water in their spectrum. I will come back to that, because I didn't show it yet to you. Oops. But what I want to do in the next 12 minutes or so is give you a deeper understanding that we reach by actually doing now very detailed modeling of these systems. And again, we have done much more than I'm showing, but I have to restrain myself a bit. So in terms of the modeling of these spectra, what I showed you so far was actually very simple slab models, as we call them. We just take a column of gas, and that can be HCN or CO2 or acetylene, and we say, oh, we have this column density of our molecule. It sits at a certain temperature, certain gas temperature, and it emits from a certain emitting area. And that produces a spectrum, because your molecular emission changes as a function of the gas temperature and also as a function of column density, because you go from optically thin emission to optically thick emission. So that is a very simple way how we analyze the spectra. All the first papers, used that method to analyze the spectra. Then we realized, well, in some cases, especially the very low mass stars, where we have like molecular emission on top of molecular emission on top of molecular emission, it becomes very difficult to analyze like one species at a time. And so we built a very fast retrieval method. This is thanks to another PhD student of mine, Phil Kuiper, the duckling code, where we do kind of a decomposition of the spectra. So we throw all the molecular spectra in at once in a huge grid of slab models. And then we allow those to change temperature and column density as a function of radius. And we put that on top of an optically thick dust midplane that makes the base continuum, and an optically thin dust surface that contains all these silicate features. And then we fit everything together in a Bayesian framework. So that allows us to really take a single JWST spectrum in and get simultaneously all the molecular column densities, temperatures, so all the properties out. But it still doesn't give us the physical and chemical insight. For that, we really need two-dimensional thermo-chemical models, as I say, because they not only set the scene, like, how is your material distributed as a function of distance and as a function of height, but they also self-consistently calculate where is which molecule sitting, how much of which molecule do I have where in the disk, and what is the gas temperature, which drives then the emission. And that is also where we learned about this layered structure, that the simple molecules CO are forming above molecules like water and CO2, and they form above HCN and C2H2. Now you can easily see that depending on how my optical depth goes, so for example, if I have a gap here in the disk, which may be caused by a planet, a massive planet, which leads to a depletion of material, of course, my emission pattern may change, because maybe I get only certain molecules emitting from here, and from here I get all molecules emitting. And because I have no spatial resolution with James Webb, all of that comes in one spectrum. And so that is the power of these 2D thermochemical models, we can not only, in principle, fit an entire spectrum using evolutionary algorithms, but more importantly, a powerful approach is to calculate grids of models and learn which parameters are actually affecting the mid-infrared spectra in which way and why. And so that is something I would like to explain now. So for the interpretation of these hydrocarbons, the conclusion was, yes, we can do it if we have high carbon to oxygen ratio. How did we come to that conclusion? Well, with a PhD student of mine, we actually expanded the hydrocarbon network that we originally had in our code. We included many longer hydrocarbon chains in order to understand where are these hydrocarbons forming in a true two-dimensional disk environment, and what could their emission be. And so you see here all the hydrocarbons that we actually detected in that very low mass star disk that I showed you in the movie. Methane being the red one here, and acetylene the blue one. And if we take a normal canonical carbon to oxygen ratio, then all the hydrocarbons form in this inner reservoir, which is the one I showed you in the sketch earlier. This is where I have high temperatures, high densities, and they love to form there, no problem. But what I really need is to push the carbon to oxygen. For example, if I go across the threshold of 1, they all start to form in the disk surface. Why is that? It's because of the CO locking. If you have carbon and oxygen in your disk, the first molecule you form is CO. CO takes 1 carbon, 1 oxygen. And now it depends whoever is left behind. If I'm in this regime, I will have, after CO formation, a lot of oxygen left behind. So I form a lot of water, OH, CO2. But if I'm in this regime, after locking my carbon and oxygen in CO, I'm left with a surplus of carbon in the gas. And those carbon atoms go and form hydrocarbons, all these CH chains. And so what we showed is really, this is super interesting, because if we drive our chemical models into that regime, we recover all the hydrocarbons that have been detected with James Webb. And it tells you, it's not a proof, but it tells you that you can form all these hydrocarbons from bottom up. There is a gas phase formation route for all of them, which is very, very interesting. And the interesting point is we also predict many more that we can now go and search for, because we need to find their spectra, their spectroscopic data, and then we can look for them in the spectrum. But also what we saw in these models, just because we go for a very high carbon to oxygen ratio does not mean we do not see water. Water is still forming. I mean, we are not removing all water. Water is still, we are not removing all oxygen. Oxygen is still part of the chemistry. And so even these models predicted that there could be some water emission. And so, of course, 2 PhD students sitting in the same office, talking to each other, how can we do this? Well, the interesting thing that then came to our realization is the moment we have hydrocarbons in a disk, so this shows you very little hydrocarbons, a low column density of 10 to the 15, a lot of water, column density of 10 to the 18, everything is fine. We see a lot of water in here, a little bit of acetylene. The moment you go to very high column densities of hydrocarbons, so make them equal, all of them are 10 to the 18, the hydrocarbons in here simply outshine any water emission. And this is simply because they are very efficient emitters. They have a ton of lines. They efficiently emit in the mid-infrared, and so they can hide the water. And so what my PhD student then did is, well, if we don't see the individual lines, we can do a cross-correlation. We know where the water has to peak, so we cross-correlate these kind of hydrocarbon-rich spectra with a template of water emission. And all of these are very low mass stars, and in most of them, we have a clear detection of water. And then, for those cases, we went back and we really convinced ourselves line by line also that we could see these lines, but each individual line is not detected at a 5 sigma level. So, but cumulatively, we know these disks contain water. Now, coming back to what is actually driving the diversity in how these mid-infrared spectra look like, we actually did a grid of thermochemical disk models, and grid here is a very moderate grid. it's only 25 models, where we varied the oxygen abundance from a factor 3 below solar to a factor 3 above solar, and the same for carbon. Basically mimicking the fact that you could have ice transport into the inner disk, and of course that changes the carbon to oxygen ratio depending on what your ice composition is. And then for all these 25 models, we ran thermo-chemical disk predictions, including the prediction of the mid-infrared spectra, the low vibrational lines. And what we did is so this is not wavelengths, but this is just the spectral footprint, the main spectral footprint of each of these molecules. So CO, this is H2O low vibrational, this is H2O rotational, the dark blue one. The red is the C2H2 and the yellow is CO2. So we simply said for all 25 models, let's put these spectral footprints next to each other. And what you see is a huge diversity that happens only if you change the oxygen abundance, for example. That is the change you see here, constant carbon and just oxygen going up. And then at the same time, you also see if you keep oxygen constant and change carbon, a lot of changes. And the interesting eye-opener was when we looked at the diagonal, because we constructed the model with that in mind. So along the diagonal, the carbon to oxygen is constant, but the individual element abundances are changing. And if you look at the diagonal here, earlier people would have said, well, the only thing that drives spectral appearance is a carbon to oxygen ratio. And that's not true. This spectrum looks different from this one. For example, in the amount of CO2 that you see with respect to water. And so it is not true that only the carbon to oxygen ratio is driving these mid-infrared spectra. What we actually measure is the individual carbon abundance and the individual oxygen abundance. And you can devise those diagnostics, so you can measure certain features of H2O rotational lines and also C2H2. And the ratio is an oxygen tracer, and you can measure certain features of CO2, and again, water rotational, and that is a carbon tracer. And then you see that those 25 models actually span nicely in a two-dimensional way, very much like this grid. Suddenly, things fall apart, and by placing your objects, those are the stars here, into that context of the model grid, you can basically read off what is the oxygen abundance of your disk and what is the carbon abundance of your disk. Now, the two are not perfectly overlapping, and the reason is that in order to generate that disk grid, we took one typical disk model. And of course, if you look at the variety of disk properties of these objects, there are a lot of things you can play with, like the disk mass, the gas to dust ratio, substructures in this. So there's a lot more. So this disk grid was never designed for any of these objects particularly, but there are enough parameters that we can tweak in order to generate better overlap. So what does this all mean? I said there is this dichotomy between the T Tauri stars, the solar type stars, and the very low mass stars. And there's a difference in the carbon to oxygen ratio. And there are two ways how we can get this. So we can either ask or say that the change in carbon to oxygen comes because of oxygen depletion or because of carbon enrichment. And the two cases go differently, because if it's oxygen depletion, we actually bring in the icy dust into the inner disk. And first you have a phase of oxygen enrichment. And then that oxygen-rich material gets accreted onto the star, and you're left behind with oxygen-depleted gas. If you look at the carbon enrichment scenario, you can think about the grains that are actually transported inwards, and once they cross a certain temperature line, the carbonaceous materials included in those grains could be freed up, sublimated, oxidized, whatever. And so we could have, from transport of dust grains, a carbon enrichment in that inner disk. But the bottom line is a lot of these evolutionary processes simply work much faster in very low mass stars compared to T Tauri stars. The reason being, first of all, the disks are smaller itself, so the physical scales over which we transport material are smaller. So given the same radial velocities, things simply happen quicker. And the same is true for the ice lines as well. The various ice lines that tell you where the volatiles sublimate, they sit much closer to the star for a very low mass star than for a solar type star. And so the distances you have to bridge from an ice line to the inner disk are also different in the two cases. And all of that makes that the very low mass stars likely evolve in terms of their chemical composition much faster than the Chitauri disk. Now, let me finish with some next steps and also some conclusions. So I think it's very clear that these JWST spectra characterize the composition of the inner disk. In fact, they characterize also the solid composition, which I had no time to focus on in this talk. But they do that in a critical period of 1 to a few million years. And that is a period where we assemble mostly the second half of the rocky planet formation. You know, the first 50% of Earth were maybe accumulated already early on, but the second part of Earth came at a later stage, which is exactly the stage we are probing here. And the second problem is the dynamical and chemical history of the disk material is encoded in these spectra in a very complex way. And so the next steps that we have to take is to really integrate the dynamical and also the chemical models. We have to go for the two-dimensional radiative transfer models so that we can decipher the information content in these JWST spectra. We are now scratching the tip of the iceberg, but we can really probe the full disk composition if we go through the 2D chemical modeling. And so I was fortunate enough to get an ERC grant, and so this is what I'm going to do over the next 5 years. I'm going to hire now 2 PhD students and a postdoc. If you know anybody, please spread the word. The job advertisement will be out soon. And next year, I can do some more hiring. So let's end with the conclusions. I think I showed you that there's a huge diversity in these mid-infrared spectra and that no two disks really look alike. We have seen many of these large hydrocarbons in the very low mass star disks, some of them even for the first time, so it was a stunning discovery. They have very high column densities, they form quasi-continua, just the molecules. And we think that this happens because the dust is more evolved, and so the opacity becomes smaller and we look closer to the midplane. We really probe almost the entire column of gas. And the disks around the Chitauri stars and the very low mass stars are very different in terms of their carbon and oxygen content. And we think at least one possibility is to explain that with different evolutionary timescales. I also showed you that the disks around the very low mass stars, even though they appear hydrocarbon rich, they still contain water. It's just, buried a little bit under this very, very emittive hydrocarbons. And then the 2D thermo-chemical model shows that if we want to interpret these mid-infrared spectra, it's not just the carbon to oxygen ratio that matters, but it's the individual abundances of carbon and oxygen that drives the spectral appearance. And so depending on how efficient transport processes are, what the composition of your ices is, etc., you can imagine that you can end up at any kind of carbon to oxygen ratio at any moment in time. And so maybe that is something that we need to explore in the future and to see whether that can really explain the diversity that we see. And with that, I would like to thank you for your attention.
Very much. Yes.
Yes, well, thanks for so exciting talk. I will ask you, particularly having in mind these first observations of and the model of the falling evaporating bodies, and having into account that the CO ratios will depend on how much water is coming and will be just in vapor phase to interact with all the rest of the components in the gas. Have you considered to make observations at different times of the same disk? Different
for variability.
To see exactly.
we have not gone back and done this. I have a vague recollection that there is one paper that did this. So at least one paper I know of, which is EX looping, because that is a variable star by itself. So people were already expecting variability, and they saw variability in the dust and in the gas, if I remember correctly. But that is, I think, still in the works. But it's very important to go back. So the variability we have seen so far and reported is from JWST with respect to Spitzer, which is 10 years. And for the dust, you can do that because the dust was good enough with Spitzer. So we saw all the silicates, and there are, in some cases, strong differences in the dust emission, and in other cases, very little. So there's a huge diversity. But the problem with the molecular emission is many Spitzer observations were not good enough to really compare now to the James Webb data that we have. But I wouldn't be surprised if there's a lot of variability in the gas as well.
Yes, because in such a case, perhaps you will also observe the differences between, if they are optically thick or thin, could be depending on the amount of dust that is there. Because what is amazing of these results is that you have acetylene and all these organics that should be catalyzed on the grains.
Yeah, so
and then vaporized.
So there are two scenarios. So what we showed with our models is we can form acetylene simply from carbon and hydrogen in the gas phase. But you're right, we have one object, for example, J1605, that was a Nature paper by Benoit Tabon, enormous column densities of C2H2 and not the same richness in hydrocarbons. And for that, one of the things we've been discussing is maybe that C2H2 could come from the grains, so basically being released from the grains rather than formed in the gas phase. In the end, I think we need both processes, and maybe they operate with different efficiencies in different systems, depending on the stellar activity, for example.
And that should be coupled with the evaporation of water at the same time.
Yes, but evaporation of water, I mean, that is in our chemical model. So we do take into account, the sublimation of the ices. That is in there. The thing that is missing, and what I also like to address in my grant proposal now, is tracking the carbonaceous content of the grains. Because that kind of, sublimation of C2H2, or however you want to call that, oxidation or erosion of grains, you need to couple between the gas phase and the solid. And that kind of chemical network doesn't exist yet. And in order to address it, you cannot deal with the dust grain with the same microscopic approach that we do with the gas and surface chemistry. We will follow a hybrid approach. Yeah.
Yeah, thanks for the very nice talk. I'd like to go back to one of the initial points of connecting exoplanet atmosphere observations to formation and this. I didn't quite see this connection. Do you think you said you'd like to see this happening? How far are we from this? Because I see so much variability. Also, most of the exoplanets that we're observing these days are hot exoplanets, typically gas giants, which have, of course, had a lot of radial migration processes, which means that they have very little contact with where they're evolutionarily formed. So what is your take on this? How far are we from being able to connect these actually?
I think in my view, not so far, because we are working on integrating the chemistry with the dynamical planet formation models, the ones that do planetesimals and pebbles, because we can integrate the chemistry in a, say, more simple way by simply tracing it as one extra component in these models. You can make your water ice or CO2 ice column density just the same as a pebble surface density, etc. So I think tracking the chemical information as an extra variable in those models is something we can do already now. Of course, the models become very time expensive, and that is the bottleneck at the moment, because if you want to learn from it, it's almost like the 2D thermochemical models. You need to run a lot of forward grids of, I can produce like, 10,000 different planetary systems, and then you have to do statistics to learn from it. And that is maybe the bottleneck at the moment, because you have to be able to run these forward models. There's no way you can invert them. Same problem that we have here. So you do need powerful computers or very clever ways of doing this to achieve a large enough grid that covers all of the parameter space to be able to learn from it. Because I think the problem is indeed that the coupling is very intricate and the parameter space is large.
In any case, my understanding is that this would be linked to the bulk properties of the planet, right?
Yeah,
then
exactly.
You have a lot of processes in the planet themselves, differentiation, and the atmosphere is only a tiny fraction of the mass of the planet.
That's true.
Evaporation. So this is challenging.
No, it is challenging, and I know the group of Christoph Mordassini and other groups as well. They try to have all this in different modules, but the simulations become monsters. So to some extent, you also have to say, I need to address this in a very specific simulation. Look at the micro physics. I would rather say, what happens interior of a planet. But then you have to be able to abstract from that and come with a simpler prescription that captures the main essence of it to be able to put it into a global simulation. I think that is, at the moment, probably the way forward. Otherwise, you create monster simulations and nobody in the end understands anymore why something comes out of it. So I'm in favor of building it up step by step.
Yes.
Okay, so to come back to what you said at the beginning, and it's slightly that the distribution of planet formation may start much earlier than the objects really. And some people actually even say that maybe for disks, the dust we see then is a kind of second generation dust that has been created by destructing the planetesimals that are left. Is there any way to look at this from a chemical point of view? I mean, do we have good arguments to say that this is likely impossible from a chemical point of view? I mean, would we expect to be able to use the chemistry that we see in these disks, as you have shown, to test this hypothesis?
Maybe a little bit. I mean, we did it. So Rens Waters and Henning, his PhD student, they looked at the PVS-70 system, where we know planet formation is already going on. And then you can characterize the silicate feature that you see there and disentangle, how much andesite, how much phosphorite you see. And what they propose as an explanation is that very likely what we see is that dust grains are actually moving in from the outer disk into the inner disk, and that change, or that explains why the feature looks like it is. So it doesn't look like the feature you would expect if everything had condensed in situ under those conditions. It looks like there was material transported from the outer disk into the inner disk, and that's what we are seeing now. It has a different composition. The problem with, whether this can be coming from parent body processing or not, very often you have, I mean, in my view, I'm not a dust expert, but what I see is that probably you have to look at minor dust species, because what we see is mainly phosphorite and the main constituents, and you probably have to look at minor species. We talked about the phyllosilicates earlier. The information could be in those minor species, which are very hard to get out of these spectra. And so I'm not entirely sure, but I think if we could disentangle the dust spectra at that level, and if we understand the opacities, maybe that is something we could try to do.
And from the molecule, you think that there is no hope in fixing the chemical richness composition of those disks to assess the cycle?
No,
the planets earlier, so it's that you go close.
Yeah.
Earlier, and only whatever was left of the planet is brought back to the gas phase later on?
Yeah, so to some extent, maybe eventually we will get there, but at the moment, the question we are asking, and we still need to answer, is what we see in the gas now, a high carbon to oxygen, does it reflect what is in the grains, or is it the complement? Because that is the question. If it comes from grain destruction, carbon going back into the gas phase. It should be the complement. And if both of them come in at the same time, then they should reflect the same composition. But that is the very first question I like to answer.
It's super difficult because most of the carbon is less than some.
Yeah, so the signature of that we see in the gas, not in the dust. And that is why we need the chemical models, including, the dust as a component for enriching carbon. But it needs to go both ways. No, the carbon can also form, because we know these hydrocarbons have very high absorption energy. So if you form them in the gas, they like to stick on every surface you offer to them. So they also just go back into the grains. And so we do need to integrate the carbon destruction, whether it's oxidation, erosion by UV, X-rays, whatever it is, we need to include that properly with the gas phase chemistry and the surface chemistry. And that will be the first challenge. And then we can answer the question whether it's a complement of what we see in the gas or not. And then we can start speculating about what you say. That's my feeling.
Very young students.
Following what I was class and also. Anyway, thanks for the talk and the results of the article. But so, is there any chance for any of these sources to have access to the ICE transmission, the absorption spectrum with James Webb, or it's no option for this?
So the classical way how we look at it is that we can get the ICE information only from edge-on disks. And in our sample, we have a handful of edge-on disks, where some of them we started to look at the ICEs now. So we have 2 PhD students, postdocs working on the ICEs. And what we can get is like the crystallinity of water ice, for example, and does it match with in situ formation, or is it transport processes? Is it inherited from the cloud? So those kind of questions we can answer. Now there is some hope. So I mean, we are working on it, but it could be that there's more for the ICEs to be found in this MIRI data than we thought initially. I'm not going to say more because it's something a postdoc is working on, and I don't want to take this away, but it could very well be that we see in the end we have to revise our idea. There's a lot of scattering in these disks. No, there was a PhD thesis of Arjen Sturm working with Melissa McClure and Evin van Disserk in Leiden, where they showed that if you want to interpret the ICE features, the scattering, multiple scattering in the disk is very important. And so that may actually make the ICE feature, or it affects how we interpret the ICE feature. It could also maybe make it more detectable than we think.
Like a second question. I think in the MINDS project, so you had some of these very low mass stars, you have the stars, but you have also some more massive curves. Are they oxygen rich or?
So we just submitted a paper on one of these Herbig disks. In general, many of the Herbig disks look very line poor, but that particular one is actually molecular rich. We still need to make up our mind, what is the real explanation. The really cool thing is, so we see water emission, but we also see SiO emission. And that could point to, SiO in the very inner disk. It's very hot, low vibrational emission. And I have a PhD student working on gravity, where we are looking at the CO emission, overtone emission. So he simply took his model and he said, what? The SiO is there. Oh, let's go for it.
So this SiO emission is coming from the dust sublimation region, or is like chalk from the.
Well, one possibility is that it comes from the dust, that it is produced in that way, but you can also form it in the gas phase under very hot, dense conditions. So again, I mean, we are with this dichotomy, and the interesting thing is, how to understand where it really comes from. So we may need shorter wavelengths data as well. We only have MIRI data now, but there's a possibility to get shorter wavelengths as well, where there's more SiO or vibrational emission to help actually, what is the temperature. We have now an idea. So it's not like super, super hot SiO. It emits at temperatures below the sublimation temperature. So it's very interesting.
So with iron, there are a couple of sources that we have this thing in SIO at much lower temperatures. Like that,
Yes.
and that also gold and refractory space.
Yeah.
And depends for massive case.
Yeah, well, you know, one of the problems we have also, that's why we have to be a bit careful in the paper as well, is, you know, we don't have the spatial resolution. You know, where's the SIO? Is it really sitting in the disk or not? We have gravity on the ground.
So I have one very generic question, not expert. So with all these oxygen rich or typical betaurits and carbon like rich on the very low mass. So I mean, absolutely. Alma, we want to measure these masses, which is the direction which proves, or is still the problem, the main problem of the disk.
It is still it's still very much debated, I would say, but there are two large ALMA programs, the DECO program and what was the other one? DECO and ExoAlma, I think was the other one, no? Where they really have incredible data on gas emission. And from what I understand, in the ExoAlma program, they actually solve the problem kinematically. No, if you have good enough kinematics, you can measure your disk masses. And they come to the conclusion that their disk masses agree with what we postulated from the 2D thermo-chemical disk modeling. And the DECO program tries to do it through very specific tracers. So a suite of different chemical tracers and to build a diagnostic based on that molecular line emission. So I hope that in the end, we all agree. And the CO problem that has been discussed so often in the literature is maybe a bit overstated, because in my experience, what I see is that what you assume about the dust properties in the outer disk makes a huge impact on your line emission. And you really need to model this more consistently to get the right answer from the CO. If you do that, even from the CO isotopologue measurements, you get the right answer. I did that study once. I analyzed our grid of disk models with that CO isotopologue method, and the masses come out correctly. It's more a matter of whether you include the dust in the correct way or not. Yeah.
Yes, one more thing. When you say very low mass stars here, when these get to the main sequence, what will be the mass of these stars?
The T Tauris?
No, the elements.
The very low mass stars.
Solar mass.
Yeah, they're about a tenth, 20% of a solar mass. That typically. Yeah.
And then this abundance, let's say, of carbon-rich molecules, does this mean anything to the amount of solids and the kind of planets that one can form around those stars?
Yeah, I think that the carbon content would be really interesting. That's why I want to figure out whether what we see in the gas reflects the bulk composition or if it's a complement of the bulk solids. Because if you were to form your planets with a very high carbon content, a rocky planet looks very, very different. If it has a high carbon content in the interior, the total interior structure, the way how it differentiates and forms a core is very different. So we would end up with planets that are not at all solar system analogs. But whether that's the case or not, we have to find out. And hopefully, fingers crossed, in a few years, we can actually figure that out. But it's very important, because I think to some extent, we already know that if the stars have slightly different element composition, that already affects the bulk planet formation. Because, you know, if you think about the stoichiometry of silicates, it's very intriguing. No, I mean, you need certain ratios. The moment your element abundances from star formation are a factor 2 or 3 different from the canonical solar ones, you get a different mineralogy. No, we ran equilibrium condensation models, and you show that you form very different minerals, and they will lead to very different bulk planet composition.
And then you have the canonical TRAPPIST-1 system, where you have 7 planets with very precise masses and radii. So and they're quite precise already, the masses and radii.
I know, but
can you really tell apart the different scenarios, let's say, using this You have several examples there.
That,
right?
that's a good question, but as far as I know, the people who do these mass radius relationships, I mean, correct me if I'm wrong, but they often do not take into account differences in composition in that sense. They do take into account, they say, what if there's more water, or, you know, in that sense, yes, but not in terms of the refractory composition. And it makes a difference for how your interior planet looks like. I'm not sure if that has been fully absorbed by that community. I would be very curious to see that.
The
Yeah.
measurements are fundamentally dynamical.
And no, the measurements are very accurate, I know. And so they are basically puzzling, you know, how many oceans do you have, or is there an ice layer, and is it this ice or that ice? But how much of that interpretation would change if you were now to assume that you have a very carbon-rich interior? I don't know. And I'm not sure anybody has really looked at that.
Thanks, okay. While we went for lunch at the JWST canteen, and you got John, you're welcome. And I remember students, you have like a 2:30 to 3:30